Okay, so I want to discuss something about intersections, which in my opinion is extremely important or at least useful, but for some reason it seems like nobody ever mentions this. And that is when working with intersections of manifolds or whatever, usually when we think about manifolds, we think about dimension. But when we're talking about intersection, dimension doesn't really matter at all. What really matters is codimension. And so that's because if you take the like x and y is subset of M, then if you look at the dimension of their intersection generically or transversely, then it's going to be some messy formula. But if you look at things in terms of codimension, it's really simple. And that is that codimensions add under intersection. And so for some examples, let's start with M is equal to R3. So if we take, for example, a sphere and a line, well, a sphere is codimension 1, and a line is codimension 2, and they intersect at some points. And points are codimension 3 in R3. So indeed, we see that codimension 1 plus codimension 2 is equal to codimension 3, which is equal to the codimension of x intersect y. Similarly, if you take, say, a sphere and a plane, both of these guys are codimension 1. And so what you find is that their intersection, which is a circle, is codimension 1 plus codimension 1, which is codimension 2. And indeed, a circle is codimension 2, while a plane and a sphere are both codimension 1. So it's fun to sort of play around with these examples and see what you can come up with. Another one is if you take two lines in three-dimensional space, then each line is codimension 1, and so their intersection ought to be codimension negative 1. Each line is codimension 2, and so their intersection ought to be codimension 4, which is dimension negative 1. But dimension negative 1 isn't really a thing, so generically they won't intersect at all. And if you look at instead M is equal to R2, then you can say, okay, if you take two one-dimensional objects, then each of these is codimension 1, and so their intersection should be codimension 2, which corresponds to points. And if you take curves, then you can sort of say, okay, both of these are codimension 1, and so again, their intersection should be codimension 2. And so when you're working in cases where you can't quite visualize it so easily, then thinking of codimension is much easier than thinking of dimension. Some other aspects which are important for codimension is when you're talking about functions. If you have a manifold which is n-dimensional and you have m functions, and you're looking at simultaneous solutions to all these functions, so in other words, f1 is equal to f2 is equal to fm is equal to 0, then in this case, the solution to these will be codimension m. And the reason being is like essentially each equation cuts out a codimension 1 object. And so each time you impose a new equation, you're increasing the codimension y1 because these are essentially the intersection of the sets f(i) is equal to 0. So if one of them defines the sphere and one of them defines the plane, then if you simultaneously set both of them equal to 0, it'll be their intersection, which is the circle. And so each time you add on these equations, generically, you're going to increase the codimension by 1, and so this whole thing will be codimension m. And so one example of a problem which sort of the parameter count that you can get from this is this famous problem of how many conics pass through 5 different points. And so the question is, why does it take 5 points to define a conic? Well, a conic is essentially determined by equations of form ax squared plus by squared plus zz squared plus dxy plus eyz plus fxz is equal to 0. Or if you don't like projective coordinates, just get rid of the z and set z equal to 1. And so there are 6 coefficients here, but you can rescale the coefficients, so it's really a 5-dimensional space. And so each time you dictate that your conic has to pass through a point, well, there can be multiple conics that pass through a point. And in particular, the dimension of conics which pass through a single point is codimension 1. Why? Because passing through a point puts a linear constraint on your coefficients. Because you say, okay, let's say that this is x0, x1, x0, y0, z0, and this will be ax0 squared plus by0 squared, and so on and so forth. So this will be some linear constraint on your coefficients, and so that'll be a codimension 1 thing. And so because this is a 5-dimensional space, because it's 6 coefficients up to rescaling, you see that in general you would need 5 different constraints to get a finite number of points. Another nice thing, if you don't understand cohomology, then you can just skip this part, is that if you want to look at intersections using differential forms or cohomology in general, then this codimension idea comes in again. Because essentially what you do in that case is you take some surface, which is some element of homology in n dimensions, and then you associate to this its Poincare dual, which is some differential form or some cohomology class, which is in h n minus n dimensions. And so here m is a dimension n manifold, which is the ambient manifold that you're working with. And so Poincare duality says that if you have an n-dimensional homology thing, then that'll give you that's a one-to-one correspondence with codimension and cohomology thing. And so if you take 2 different manifolds, then for example, this will be in HM1, this will be in HM2, and these will correspond to say omega and nu, which will be in Hn minus m1, and this will be in Hn minus m2. And then you can take the product of these, and if the product of these will represent some other cohomology class, and take the Poincare dual of that again. So if you look at omega wedge nu, or omega times nu, and then again you go through Poincare duality, then what this will correspond to is the intersection points of the intersection of these two guys. And why is that? Well, because if you multiply these two guys, the dimensions here are essentially the codimensions of your spaces. And so the dimension of the wedge product is going to be the sum of the codimensions. In other words, it's going to have the codimension of the intersection. And so at least you can see by a dimension count that the statement that the product of these two Poincare dual cohomology classes gives you something corresponding to the intersection makes sense. Okay, so another cool example, which maybe is a bit more difficult to visualize if you don't talk about this codimension thing, is you can use it to analyze singularities of certain objects. So for example, you can look at the equation y squared equals x cubed. And so you can open up Desmos and you'll see that the graph will look something like that. And so over here you have some sort of a singularity. And so you can ask, okay, what can we say about the singularity? I mean, really, like, topologically, this sort of looks like a line. So in what sense is this really a singularity? And so you can ask, okay, maybe looking at the picture of the real numbers isn't too great. Maybe we should look at the picture of the complex numbers. And if you look at the picture of the complex numbers, what you get is something like this. So you get something which is topologically a sphere, except it has some sort of a singularity over here. And so one way to think about this is that this really ought to be an elliptic curve. So it really ought to look like a donut, but it has a singularity, so the sort of it isn't a genus 1 surface, but instead it's some deformed thing. So if you look at y squared equals x squared times x minus 1, then this curve will look like this, and the corresponding complex picture will sort of look like a pinched torus. But over here, like, so this point over here corresponds to this point over here, and you can see that you sort of have a little branching from this. But over here, you don't quite have that because you have just a single point of singularity here. So what this really does is it takes this whole loop and it sort of moves it over to here, and it contracts this point as well, and it pinches that entire thing into this singularity over here. So how can we analyze the singularity? Well, the singularity happens at x equals y equals 0. And so what we can do is we can take the unit sphere S3 in C2, or I guess not, I won't take the unit sphere, but I'll take the sphere norm of x squared plus norm of y squared equals 2. And the reason for that is just for convenience of equations. But this defines some sphere in C2. Why? Because this is one equation in a 4-dimensional real space, or a 4-dimensional considered as a real manifold. And so if you constrain one real equation in it, then you get a codimension 1 space, which is a 3-dimensional manifold. And so, you know, x is equal to x1 plus ix2, and y is equal to y1 plus I y2. And so what this will actually be is x1 squared plus x2 squared plus y1 squared plus y2 squared is equal to 2. And so if you take the sphere, then this will look something like this in four-dimensional space. This will be some surface in four-dimensional space. So this will be dimension 2, and this will be dimension 3. And you can look at, okay, if you have the sphere which is around the origin, then what will the intersection of the sphere look like with this singular curve near the singular point? So as I've been saying, dimension isn't really useful, so what you want to do is look at codimension. So this is codimension 2, because it's a dimension 2 thing. It's one complex dimension, which is 2 real dimensions, and because the ambient space is 2 complex dimensions or 4 real dimensions, this is codimension 2. And this is a dimension 3 thing, which, as we've sort of seen, is a codimension 1 object. So that means that their intersection, the intersection of this 3 sphere with this curve, this complex curve, is going to be codimension 1 plus codimension 2, so that's codimension 3. Or in other words, a one-dimensional object, so it'll be some sort of a curve. And so we can try and analyze, okay, what does the curve look like? So we can actually explicitly parameterize the curve, because if you say x is equal to e to the 2it, and y is equal to e to the 3it, then we can see that satisfies this equation because both sides are equal to e to the 6it. And it also satisfies this equation because both x and y have norm 1, and so the sum of their norms is 2. And that's why I chose 2 instead of 1. And so you can try figuring out what this is, or you can write this as like cosine something, sine something, and then similarly for this. And so now you have 4 different coordinates. And the thing is that S3 is the same as R3 plus a point at infinity. So you can use the stereographic projection to convert these equations into R3. And now Desmos has 3-dimensional graphing capabilities, so you can actually just graph out what this looks like. And you'll find that what you get is a trefoil knot. So what this says is that this curve near the singular point looks like a trefoil knot. And why does this indicate to us that this is a singularity? Well, if it was a non-singular point, then the intersection should look just like a simple circle. Why? Because you can check that I chose the sphere with a norm equal to 2, but you can check that no matter how small your sphere goes, the intersection will look like the trefoil knot. But if it's a non-singular point, then near any single point, the surface should look like a disk, and so the intersection should just look like a circle. But because the intersection looks like the trefoil knot, we can see that it isn't the circle, and so we can sort of analyze the type of singularity we have by sort of computing what this intersection looks like. And so another neat little application of this is something called the Briscorn, I hope I spelled that right, spheres. And so this is similar. You take a higher dimensional complex surface and you intersect it with this codimension 1 sphere, real codimension 1. And these have the property that they sort of are like these Milnor spheres, which are homeomorphic to Sn but not diffeomorphic to Sn. So maybe an easier exercise that you can do is you can try and look at, okay, if we look at the equation y to the n equals x to the m for n and m natural numbers, then what does the intersection, this one will also have a singularity at x equals 0. And you can ask, what does the singularity look like when we intersect it with a small sphere around the origin?